Okay, dear teacher friends, we are beginning our day's proceedings. So we have with us Professor Biman Nath, who will be giving a brief glimpse about electromagnetic spectrum. Before we proceed, I take this absolute pleasure in introducing Professor Nath to all of you. He is a senior faculty and a theoretical astrophysicist. He joined RRI in the year 1997. Some of his major research areas of interest are um, cosmic rays, evolution of universe. Professor Nath earned his PhD from University of Maryland, the United States of America. He completed his postdoctoral studies from the Max Planck Institute, Germany, and the Inter-University Center for Astronomy and Astrophysics in Pune. Sir takes deep interest in science popularization, and that's why he's frequently traveling, giving talks and popular sessions to teachers and general audience. It's lucky that we have him here today for all the teachers here. For any of you who is a frequent reader of Bengali newspapers, Professor Nath would be a household name. He regularly writes for newspapers. Apart from that, he has also authored several books, and some of the titles, if I may read: The Story of Helium and the Birth of Astrophysics, Nothing is Blue, Homi Bhabha, a Renaissance man among scientists, A Tattooed Fakir, and many more. Let's all warmly welcome Professor Nath. And he's a great storyteller. I hope you'll have a great 1 hour listening to him. Over to you, Professor Nath.
Thank you, Anjali. And good morning to everybody. I am, as Anjali said, I am mainly a theoretical astrophysicist. And looking at the subjects, it was suggested by Dr. Subramaniam, and I also thought it was appropriate that I could talk about electromagnetic spectrum. But that might be a bit from an astrophysicist's point of view. So you might get something, I don't know, I hope you get something which can be told which could be communicated to school students, and which might complement what they would study from their textbooks anyway. So I have some slides, but I would like it to be more interactive, so please feel free to stop. And how much time do I have? It's 1 hour. So, but the slides, I don't know how long it's going to go on, but we can discuss in between also. And so I thought first I will start with electromagnetic waves. It's been a while I have looked at the textbooks and what exactly is done in, for example, H.C. Verma's book and other textbooks, NCERT books. So let me start with electromagnetic waves, the basics of, and then we will go to different frequencies and how, at least in astronomy, we make use of electromagnetic waves in different frequencies and what knowledge we get. So electromagnetic wave, as you know, can be thought of as a self-sustaining sort of a wave produced by oscillations in a charge, for example. So if we think of, I remember doing this when I was teaching my son when he was in class 11, 12. So that's from the memory. I thought this is one way I could communicate to him, and this is how I had learned how the basics of electromagnetic waves. So one can think of a current carrying wire, and then one knows from Biot-Savart law that it produces a magnetic field, right-hand rule, the current going this way. So you have the magnetic field shown in the in blue here. This is the magnetic field, and this vector, the tangential vector, basically shows the direction of the magnetic field. And now, suppose I have, instead of a DC current, suppose I have an AC. So the direction of the current is going to change, and suppose the direction of the current now changes, which is going to change the magnetic field direction, right? Earlier it was like this, now it's going to be like this. So that introduces as a change in the magnetic field. And we know from Faraday's law that the change in the magnetic field induces a EMF, right? So a change in the magnetic field induces an EMF. We know the directionality. One can think of it as like going through a solenoid and then producing an EMF. That we know that. So because of this, then the change in the magnetic field is going to induce an electric field, so that on the circumference of a sort of a vertical circle are oriented clockwise related to the magnetic field change, right? But that itself, in turn, introduces another change. There was no electric field, now there is electric field. So that's also a change, and that introduces another magnetic field from, again, Biot-Savart's law, right? So this Biot-Savart's law and Faraday's law continue. So change in the magnetic field produces electric field, change in the electric field produces magnetic field. And since I am oscillating the current, the charges are, the motion of the charges is varying. So that produces a wave of, so this produces a magnetic field again, and that produces, and that process continues. And that's how the wave propagates, right? And if I can just take the circles away and look at the vectors, this is how things would look, the electric vector and the magnetic field vector. And interestingly, they're always in phase. And that's just a consequence of the two laws, the Biot-Savart's law and the Faraday's law. There it's always in law. And the wave propagates in a direction which is perpendicular to both electric field and magnetic field, and given by the cross product of the direction of the cross product of E cross B. Right? We know that. And this only shows certain instantaneous vectors. We can fill up the gap, and we can see that this is going to be like this. So it's like a sinusoidal variation in the electric field and concomitant variation in the magnetic field, which is perpendicular to one another but in phase, right? So, and the propagation, as I said, is given by the direction of the cross product of E and B, right? So you know that. So this is where I saw sort of animation, yes, which might be helpful. So this is the electric field, and this is the magnetic field direction, the two perpendicular direction, and that's how one defines the wavelength, right? So then we have an electromagnetic wave that is propagating. So in a way, I have varied the direction of the charge. Going to a more fundamental, this is one case of a current carrying wire, and then I have AC current. Suppose I go to a more fundamental understanding of what produces an electromagnetic wave. That is then going to lead us to an understanding of the fact that an accelerating charge, if you accelerate a charge, then it's going to produce an electromagnetic wave. Just a current carrying wire, if I don't vary the current direction, I'm not going to, just a current carrying wire is not going to produce an electromagnetic wave, because this is just a charge going with uniform velocity. I have to change its direction, which means there will be an acceleration. Changing the velocity, so changing the direction or somehow decelerating, accelerating, that's going to produce electromagnetic wave. And one can understand it in a way, I believe it was first suggested by J.J. Thomson, the discoverer of electron. He suggested a way of looking at the electromagnetic wave this way, and it has relativity in its heart. So, for example, I have a charge here, and I know that the electric field is going to be like this, okay? And we know the electrostatic field goes as 1 over r square, etc., right? Coulomb's law. Now, suppose this charge is moving, and it would have reached this place, okay? If it were going with the same velocity that it has been moving. At the far field, they want, and I have what has happened is, instead of letting it move with this same velocity, we have somehow stopped it, retarded it, decelerated it. Okay, so the charge is stopped here. Okay, now very far away, the field, the space will not have this information that the charge has been stopped. And just the fact that no communication, no signal can propagate faster than light. So there is going to be a boundary beyond which the regions will not have any information that the charge has been retarded, the charge has been decelerated and stopped. So the field there will be oriented like this, whereas the near field will be oriented like this. This is a very, very schematic diagram. Actually, there will be curves and all that, but it's a very schematic diagram. And as you can see, there is going to be a boundary where the fields are going to be compressed. And that this boundary is going to propagate with the speed of light, just the way the information is going, right? And that is the electromagnetic wave. And that is one way of understanding why acceleration of charges or deceleration or whatever leads to the propagation of electromagnetic wave. One can also understand one thing. We know that electromagnetic wave, the light that we go, the energy falls as 1 over r square, which means the electric field falls as 1 over r, because the energy is proportional to E square or E cross B, right? The Poynting vector. Now here, that is a puzzle, right? Here the field lines, the field falls as 1 over r square. Here the field falls as 1 over r square. So the wave energy would have fallen like 1 over r to the power 4. But the wave energy falls as 1 over r square, which means the electric field in the wave falls as 1 over r. Why? Because of this compression. It is 1 over r square here, 1 over r square here, but 1 over r here because of the compression. And that is a very, very cute way, I thought, of looking at the electromagnetic wave and understand it from the point of view of relativity. And on the boundary layer. And one can actually work out these angles here from relativity. You can actually find, for example, this is an example that is given for certain velocity. It's a very relativistic, you have to, if you move the electron in a very high velocity, then only, you know, the angles become so different and you can see it. So anyway, the angles can be calculated using Gauss's law and relativity, basically. Okay, so then if we now know that the acceleration of charges basically leads to propagation of electric wave, and I'll start from there. There are many different contexts, different physical processes where one encounters this, that charges are accelerated or decelerated, or I'll give you some examples from astronomy. So before going to astronomy, so this is one example where one sees this. Suppose I have an ion here and I have an electron. Ions are heavy, so they don't move around much, so I can think of it as like more or less stationary. Electrons are very light masses, so they move around. In a plasma, that's what's happened. Ions don't move around. It's the electrons which, you know, go around. So suppose there is an ion here, and the electron is moving, and when it comes to the electrostatic field of the ion, it gets bent here. It just gets focused here. Now that's acceleration. It's the change in the direction of its velocity, right? So that's acceleration, and acceleration of charges leads to the radiation of electromagnetic wave, and it's going to radiate. It's going to lose some energy because it's going to get some sort of kick in the direction, right? So it's going to lose some energy, and one can find out what's the energy of the wave or the photon, whatever you may think of it. This is what is called the so-called braking radiation. The electron is sort of putting on a brake as it is moving. So, and that the word for it is Bremsstrahlung, is the German word for braking radiation. Brems and Strahlung. Strahlung is radiation. Now this is, I think, another. It shows that it's yeah, as it is decelerated, then radiation comes out of it, right? Now. One knows that, you know, this is what is employed to get X-rays out of X-ray tube. You know that, you know, you have a cathode ray gun, and you have some sort of target, and the electrons come out of it with a very high velocity, and in the target you have heavy nuclei, and so the electrons are basically retarded, and you get X-ray out of it. In the X-ray tube, also some other photons come out of it. That's because of quantum mechanical description. Now, this description that I showed you, this is totally classical. This is classical wave. There's no quantum mechanical consideration here. But you also get radiation from quantum mechanical consideration, where classical ideas don't really work, right? So in a quantum mechanical model of an atom, you have the nucleus and the electron shells of different energy, and the transitions between different energy levels leads to radiation of energy. When the electron falls from a higher energy to a lower energy level, it radiates, and it goes from lower energy to higher energy, it absorbs. So now that's another description of, this is not classical. Classically, you cannot think of this. So anyway, we're not going to talk about quantum mechanical aspects here, but I thought I should mention that in X-ray tube, although you also get this radiation. Now this radiation is a continuum radiation, basically meaning that you get radiation of different frequencies, because there are electrons moving in different velocities, and the impact parameter, I mean, it might come very close to the nucleus and get bent very sharply, or it might just graze to the boundary of the atom, and then it may not get bent so sharply. So its velocity may not change much, its acceleration, deceleration may not be much. So you will have radiation of different frequencies, right? Continuous radiation, right? So you have a continuum spectrum. If you take a spectrum of this radiation here, you will just see a blue to red, I mean, like all kinds of radiation, no line there. But you will also get line because of quantum mechanics. Because what might happen, an incoming electron might hit an electron here, eject it out, and then create a empty place here for an electron to jump and then radiate an electron. But that will be one particular frequency, right? So you will also have such quantum mechanical line transitions in such a case. I mean, so the case is that of a X-ray tube where you have cathode ray gun and you have target, right? So you have both, and the spectrum will look like this. So you will have some spikes, which is because of the line radiation, and these are called K alpha, K beta. Basically, this is called the K shell. The innermost shell is called the K shell, and if you have a transition from just beyond that to the K shell, then you have K alpha, and from here to here it will be K beta. Anyway, so this is one particular case of X-rays from some target, like I've taken molybdenum here. And so, but you will also have, most of the radiation is, by the way, Bremsstrahlung. This is the continuum radiation, most of the radiation. It's about, if you look at the energy, it's about 70 to 80% is coming out of the X-ray tube. Now, one can think of then, so this is for electrons coming out of the electron gun and hitting a target, right? And as I said, depending on the impact parameter, right? How impact parameter is the perpendicular distance. If it were to continue in the same direction as it was coming from the infinity, then this is the perpendicular distance. So depending on the targets, positions of the targets and the electrons, there will be range of impact parameters, so there will be range of velocities. But the electrons may also have different velocities. Suppose I have a plasma now. I have a very hot plasma where I have, suppose there is a fixed temperature. It's some sort of a steady state temperature, thermal equilibrium. So the particles will then have a velocity distribution, Maxwell-Boltzmann distribution. So then I will need to fold this with the velocity distribution of electrons and then calculate the total spectrum that I'm going to get out of, suppose I have a hot plasma at say 1,000,000 degrees or 10 million degrees gas. What is the radiation that I'm going to get, and what will be its spectrum? One can do this calculation. It's actually tedious, but in principle it's not difficult. It's just to fold in this with the Maxwell-Boltzmann distribution of velocities, and then you get a spectrum like this. So this is the spectrum of electromagnetic waves that you expect from a hot plasma at different temperatures. So there's some. So this is, I knew in log, and this is log of frequency. I nu is basically the specific intensity, basically energy per unit area, per unit time, per unit frequency, per unit steradian. That's the typical, that's the parameter that we in astronomy use for certain reasons. It's a very fundamental parameter. So anyway, so this is how the spectrum looks like. This is the it's called the thermal bremsstrahlung radiation, because the gas that I'm expecting this, calculating this bremsstrahlung radiation from is at a given temperature. It's in thermal equilibrium. So we call it thermal bremsstrahlung radiation. Now here, let's look at the shape of the spectrum and then try to understand. So one thing that we notice is the higher the temperature, the intensity grows at a certain range of frequencies, the intensity grows. Now then there is a cutoff. This cutoff is an exponential cutoff, and that comes because of the exponential cutoff in Maxwell-Boltzmann distribution. Because although the electrons have a range of velocities, but there is an exponential cutoff beyond say the e to the power half mv square over kt, right? Beyond that, you won't have many electrons there. So they will not be able to produce photons beyond a certain value. But this comes about around where h nu is of the order of kt. That cutoff comes. And so this is well understood. Here is something else is happening. You might wonder what is happening here. What happens here is slightly more subtle. It has to do with the blackbody radiation. Basically, at low frequencies, if I have a plasma, the radiations there, depending on the electrons are also absorbing the photons that they're producing themselves, right? So this plasma is not just a ball of just particles. There's also radiation there, and one has to take into account the matter radiation sort of interactions. And so one has to take into account the absorption coefficient and the emission coefficient of the electrons given the radiation, and that changes with frequency. At low frequencies, the absorption coefficient increases. It's very easy to absorb. And Kirchhoff's law basically says that if there is a thermal equilibrium, which means matter radiation equilibrium, when matter and radiation has come to an equilibrium, in the sense that electrons are radiating, absorbing, radiating, absorbing. Radiation is being emitted, being absorbed, right? And if there is an equilibrium, then we know what the spectrum is. That's a blackbody spectrum. So at very low frequencies, when the absorption is very, very efficient, then this plasma, ball of plasma that I have imagined, right, is going to produce its radiation, but it's also going to absorb its own radiation. It's going to become a blackbody. So that at very low frequencies, one should expect a blackbody kind of thing. And blackbody, in Rayleigh-Jeans part, it goes as the Planck goes as nu square, proportional to nu square, and this is actually nu square. So that's basically because it is self-absorbed. It's absorbing it itself. Okay? And I'll show you some examples from astronomy. We see both of these at high frequencies and low frequencies from astronomy. So let me go to the high frequency first. So this ball of plasma that I have been talking about, this can be visualized in terms of, for example, when you look at clusters of galaxies. So there are galaxies which, galaxies are the building blocks of the universe, and there are billions and billions of galaxies. And they're not distributed uniformly. There are clusters of galaxies. There are loose clusters, there are rich clusters. So where, for example, hundreds, sometimes thousands of galaxies are packed in a certain volume. That produces a potential well, a pretty high potential, a pretty deep potential well. And because of certain, for example, there's a lot of gas also in the universe, okay, leftover gas. So this gas gets trapped into this potential well and becomes heated because of the depth of the potential well. It's called the virial equilibrium. So you can think of it as like where the kinetic energy of the particles, also the galaxies, being indicative of the depth of the potential well, GM over R, say, right? So where the kinetic energy is comparable to the potential energy. Given the depth of the potential well, the speed of the particles is of the order of 1000 kilometer per second, 1000 kilometer per second, which would translate to a temperature of, given electrons, temperature of about 10 million degrees. So that I have a plasma of electrons, that this is very high temperature, so it's all going to be ionized, whatever element may there be. So it's an ionized ball of gas then that I have. Now this is what it looks like in X-ray. This is what it looks like. The same cluster. It's a cluster called Abel 2029. It's just from some catalog that Abel created, listed, and so these are the galaxies that shows up in optical. If I look at these cluster with optical telescope, and so what it doesn't show in optical is that there is a lot of gas here. This gas is hot, okay, and shows up in X-ray because that gas is producing Bremsstrahlung radiation in X-rays, right? So it's so hot that this is where we see these X-rays. So this is, for example, taken an image taken with Chandra X-ray telescope. In this was very known very early on. This is 1970s. This is observation of Coma cluster, which is a nearby cluster of galaxies in the direction of the Coma constellation in our sky. So it's called the Coma cluster. And with X-ray telescopes in 1970s, people saw this spectrum, detected this spectrum. One can look at the spectrum of this gas, and this is exactly what one would have calculated like this. So one can fit this spectrum with, so you can try fitting and then find out its temperature, because I know where if this is exponential drop, if I can try to fit, I can estimate its temperature. This is how, for example, they estimated the temperature of the gas in the clusters of galaxies. So this is Bremsstrahlung radiation, and this is thermal Bremsstrahlung radiation. What about the low frequency? Let's look at this picture again. This is low frequency. Now, low frequency, this is going to be so low. This is the range of frequency, right? This is going to be so low, it's going to be even below optical. So we'll have to go to radio. So when you look at radio wavelengths, for lower temperature, suppose if I go to a lower temperature, then it's going to be, the line is going to be like this. And in radio, I'll show you this rising curve. So for that, I'll take the example of the emission nebula in our galaxy. Now there are regions in the galaxy. So the galaxy has stars. It also has gas around stars. Now if I have a very massive star which has surface temperature very high surface temperature, which means it emits UV radiation. So this is a nebula. It's the Orion Nebula. You may have seen the picture. It's a very famous picture of Orion Nebula. This is in the Orion constellation. You know that below there are 3 stars in Orion, and below the belt you will see another 3 stars, and the middle is the Orion Nebula. It's not a star. It's a nebula. Basically, it's a region of full of gas, but there are lots of young stars. The young stars are more likely to be massive stars because massive stars don't last very long. So these massive stars are there embedded in this gas, and the UV photons from these massive stars ionize this gas and heat it up to about 10,000 degrees. So this gas is at a temperature of 10,000 degrees. So it's again a plasma. Again, it's going to radiate Bremsstrahlung radiation, but it's high density. Okay, so it is likely to be again self-absorbed, and this is the radio spectrum of this nebula. For example, in radio, this is in megahertz. This is 100 megahertz. This is the gigahertz, and you can see that there is a drop off here because the gas now is absorbing the own radiation that it is producing and becoming like a black body. So this is basically Bremsstrahlung in a range of frequencies from very low to very high frequencies. And we see examples of all of this in astronomy. Which is why, astronomy is a very interesting way of introducing basic physics. You see, in astronomy, we deal with a range of physical parameters, range of temperatures, from very cold gas to extremely high temperature gas, like densities from very low densities to extremely high densities, right? And what are the other parameters? The pressures, very low pressures to high pressures. So, which is why I think astronomy is a very very useful tool to introduce a lot of this basic physics to the students. Anyway, let's talk about some other kinds of radiation. Now we talked about acceleration and the deceleration of electrons in the presence of ions. That happens in a plasma. I can accelerate the particles in a different way. Suppose I have a magnetic field. Then we know from Lorentz force, I think they do this in cyclotron concept is there, right? All right. So the charged particles are going to gyrate around magnetic field. So suppose I have a very straightforward, for schematic diagram, I have a magnetic field like this, and an electron moves around like this. Now that's also acceleration, right? The direction of the current, its motion is changing all the time. Its speed is not changing, but its velocity changing. So there is an acceleration there, right? And so it's going to radiate electrons, photons, right? And that is called cyclotron radiation. And if it happens at a very high speed, then there's some relativistic effects are going to come in there, and we call it synchrotron radiation. Right? And depending on basically the energy of the electron, the energy of the electron is very, very high, then the motion is going to be at very high speed. Then there's going to be two effects. One is the time dilation effect, and there's a focusing effect, the beaming effect. And that produces what we call the synchrotron radiation. And one can work out, now for this we need very, very high energy electrons. And those high energy electrons may not be in a thermal equilibrium because the interaction cross section decreases with speed. So if you had very high energy, high speed electrons, they're not going to interact very much. So you may not have a Maxwell-Boltzmann distribution for that. What is likely is a sort of a power law distribution that is shown, for example, for cosmic rays. This is the spectrum of cosmic rays. These are high energy particles that keep bombarding us on the Earth, and they're produced in astrophysical objects and phenomena, very high energetic explosive phenomena like supernova. And so you can see that this is the energy distribution. Number of particles, this is the energy, and on the y-axis we have number of particles per unit volume. This is a flux though, but one can convert into also per unit energy bin. So just like the Maxwell-Boltzmann distribution would have been like this, but we have a power law distribution. So what happens then? My calculation of the spectrum is going to be now different. I have to fold it in that my seed electron energy distribution is not Maxwell-Boltzmann anymore. So from a single energy electrons, I would have gotten a radiation like this. A single energy electron would have given me a synchrotron radiation like this, depending on the energy. But since I have many such electrons and the electron distribution is like this, I will have many such radiation from all these electrons, and so ultimately I will have a synchrotron radiation spectrum, which is a power law. This is log. Again, in astronomy, because we deal with a range of parameters, we are fond of plotting log, because otherwise, we can't really describe all these, ranges, a huge range of results. So that's the final synchrotron spectrum, and this is, for example, one can encounter this in phenomena like this, where, for example, this is an explosion. This is in Crab Nebula, in the direction of the Crab constellation. So we know that this is the result of a supernova explosion that happened in 1054 AD, and so this huge explosion basically accelerated electrons, and there's a huge magnetic field, and this produces synchrotron radiation. Let me show you the spectrum that you get from this Crab Nebula. This is the spectrum of radiation that you get. This is X-ray, this is soft X-ray. These are from different observatories. Again, this is where things are getting self-absorbed. So it's again, declines like this. At high energy, this is the power law that I've been talking about. Okay, the radiation has a spectrum, which is a power law, and that you expect from synchrotron radiation. You also see gamma rays, but that's a slightly different story. I'll tell you what produces gamma rays. Okay, I do have. So this is another way of looking at. So gamma rays, where you have very high energy photons and very high energy electrons, you need to have quantum mechanical scenario, because now you're thinking of photons as billiard balls, right? So, for example, this is how one of the ways where gamma rays are produced. So, this is a proton, for example, high energy proton. It interacts with a proton. Oh, this is a proton, and then they produces 3 pions. The neutral pion then decays into gamma rays, a few GeVs. Okay, these are the gamma rays. This is how gamma rays are produced. Okay? And so the spectrum that I showed here, some of the gamma rays are produced in this fashion. Some of the gamma rays are produced in another way, where these synchrotron photons are boosted by high energy electrons to high energy photons. So you know Compton scattering. Compton scattering, what happens? I have an electron, I have a very high energy photon. It comes, we show this as a billiard ball kind of a calculation, right? I have an electron, more or less stationary, and I have a high energy photon, then it gives an electron a coil, then photon loses some energy, right? This is Compton scattering. The inverse can also happen. I may have a low energy photon, I have a very high energy electron. So then I need to go to the rest frame of the electron, and then I will see that a very high energy photon is coming to me, just because of Doppler shift. And then I will do from the point of view of the electron, it's having a Compton scattering. Okay, then I come back to again the lab frame here. You'll see that basically the energy has been transferred between the electron and the photon. The high energy electron has given the energy to the photon and boosted some of these low energy photons to high energy. Some of the gamma rays are produced by what we call inverse Compton scattering. Okay. So these are different physical processes that are happening in the astrophysical context. And so when we look at the spectrum, we need to look at the spectrum from radio to optical to X-ray to gamma rays in order to get a sort of a holistic view of the whole object or the phenomena. What are the different processes that are happening? So I showed you this. Of course, and then there are line radiations, which come from quantum mechanical consideration. As you know, different electrons, there are energy shells, and the transitions between the energy shells give you the lines, photons, and different elements have different signatures. So looking at the spectrum, we can identify which element it is coming from. Right? So this is a very useful tool for astronomy. Now we see the line radiation from, I said, the emission nebula, the gas around massive stars that I showed you. I talked about only the Bremsstrahlung radiation at that time, but you also see line radiation from there. It's a very interesting phenomena. What happens? So I have a massive star here, and I have the gas. So the UV photons coming out of this massive star, hot means what? The surface temperature is in excess of 10,000 degrees, like 30,000, 40,000 degrees, the surface temperature. So it's creating UV photons, which ionizes the gas around it. Right? Suppose it's just hydrogen, then you need only 13.6 eV, right? Which is of the order of 10 to the power 5, right? If you just correct. But so you can ionize this. So suppose it's just hydrogen, right? So the gas is ionized. So I have ions, which means the hydrogen proton and the electrons moving around. Once in a while, it will get trapped, and then basically it will recombine. It will recombine into an atom again. So the electron comes in and falls into one of these very outer energy levels, and then it cascades down to lower and lower energy levels, right? And at the same time, it's producing radiation. So you see line radiation from this emission nebulae also. This is a collage of different, lots of different nebulae, and you can see certain colors are prominent, very common here. One is red, and the red color is coming from the hydrogen. Hydrogen has this important radiation. This is the n is equal to 1. So all the transitions here are the Lyman series. All the transitions coming to the n is equal to 2 is Balmer series. So the Balmer 3 to 2 line is very important for astronomy. What happens? So the electron comes here and then cascades down, and in the 3 to 2 level, as you can see, this is the wavelength of 656 nanometer, which is in red, basically 6560 angstrom, right? And that's the red color. This is the red color coming from hydrogen, 3 to 2 Balmer line. Okay, there are other lines also, which are also very interesting. Some of these lines are not seen in laboratory for a very interesting reason. And when they were first seen in 19th century, people thought they were from different elements. Oh, I've discovered a different element. And people kept giving the names like nebulium and things like that, which later people understood that it's not different elements, but the lines which you don't see in terrestrial laboratories because of a very interesting phenomena. So what happens, these lines, so the electrons are at a certain excited level, right? And it has to come down. But it has a certain time, right? The residence time, the lifetime of an electron at a different level. We know it from quantum mechanical, the uncertainty principle, delta E, delta T gives you the lifetime. Right? So it has some lifetime. But in terrestrial situation, with the density from Avogadro's number, you can figure out per cc there are 10 to the power 19 molecules in, right, in one cubic centimeter. Whereas in these densities are ridiculously small. This is per cc, you will have about 1 or 10, maybe 100. Okay, that's like the typical densities here. So what happens in terrestrial cases, the electron is there at a certain excited level. Before it can radiate, it gets knocked down by collision. So you don't see that line. Whereas in low densities in astronomical situation, there is not much of collision happening because of the low density. So the electron can hang around for a long time and radiate in its swing type. So you see that line. So these lines, for example, this is this green line, you can see the green line is from oxygen, doubly ionized oxygen. And so these were identified later when people understood quantum mechanics, etc., etc. So these are interesting, stuff. Oh, right. So this is, for example, a particular nebula, Eta Carina nebula, and this is the spectrum. Now, these are the hydrogen lines, H beta, this is H alpha, this is the red line. Of course, this is a very prominent line, I told you. So the red line, which is why most of the emission nebulae look red, because of the hydrogen, the Balmer line. But you also see some, this is the O3. O3, this is how we write doubly ionized oxygen. This is around 4,900 angstrom, it's a green line. And that is, we call it forbidden. It's not really forbidden. You just don't see it in the terrestrial situation because of the high density. But that shows up in low density astronomical situations. It's very interesting stuff that you, again, it's a very basic quantum mechanical stuff which you can teach through astrophysics. Okay. Now, in the last few minutes that I have, I'll run through some objects. I'll show you images and spectrum in different wavelengths. This is why we study objects in different wavelengths with a multi-wavelength astronomy. And earlier it was not possible to do this because of detector technology was not sophisticated enough. In many cases, for example, it's very difficult to detect infrared lines, because of the water vapor. Either you have to go high up in the mountains, or you have to go to a desert-like environment, or you have to go beyond the Earth, right? And to detect infrared is very difficult. I mean, now we have CCDs, but you have to cool the CCDs, right, to detect the infrared, which has been possible, which has become possible only in the last like 30, 40 years or so. So that has given a boost to the multi-wavelength studies of. So for example, this is sun and different wavelengths. And so let's forget about these three. This is at 1007 angstrom. Now, different wavelengths will tell you a different story. For example, this is a very short wavelength, right? This is the shorter the wavelength, the higher the energy, and you're going to probe higher energy events. So the solar flares, for example, will show up in shorter wavelength stuff, right? Higher energy events. Like the h nu is then higher, right? The lambda is shorter here. And so, for example, the solar flares, these are where the sunspots are there, and flares are happening here. And so all the short wavelength are going to tell you this. Let me give an example of galaxies, how galaxies look at different wavelengths, for example. So this is one galaxy. It's a nearby galaxy face on. It's called the Whirlpool galaxy. Astronomers are fond of giving very colorful names. So this is what it looks like in radio. In radio, most of the radiation is coming from a particular line radiation from hydrogen. The rest wavelength is 21 centimeter, and it's radiated by hydrogen in its ground state, because in its ground state, what happens, has only one electron, but the electron can have a spin which is either parallel to the spin of the proton or antiparallel. So there is a flip. If there is a flip, then you get a radiation like this. And this is the bread and butter for most of radio astronomers to detect 21 centimeter radiation. So this basically shows the distribution of hydrogen gas, okay, coal gas, okay, in the galaxy. So this is basically coal gas. The radio waves reveal the regions of gas cool enough for also molecules and atoms to exist. Then suppose we see this in infrared, okay. Now stars come in different sizes, hot stars and cool stars. Hot stars, as I give you the example of tens of thousands of degrees surface temperature, right? They have a spectrum mostly weight towards the UV. Low surface temperature stars, for example, 4,000 degrees or so, they're mostly reddish, red giant stars and reddish, right? So these are the cool stars. So if you look at infrared, for example, at 1.2 microns, so this is near infrared, so you'll see only cool stars, right? So and there are more low mass stars than high mass stars. So in infrared, we basically get to measure the total stellar content of galaxies. Okay, then we see optical, for example, and optical basically light comes from the stars which have the size around the sun. Right? Typical. Ultraviolet, right? That coming from very hot stars. So hot stars are massive stars, and massive stars don't last for very long. So they're also young stars. So when you look at a galaxy in UV, for example, our AstroSat, the satellite that was launched in 2015 by India, it has a UV telescope called UVIT, and that regularly looks at UV radiation from galaxies. So you're looking at regions where star formation has happened recently. These stars have not died yet. So hot stars, UV, young stars, and this is recent star formation. Then you look at the X-ray, then you see energetic phenomena. So, for example, there may be a black hole there. There are black holes around, and when the gas falls into the black hole, it becomes very hot, 10 million degrees or so. It will produce X-rays. So, looking at different wavelength, right? This whole spectrum gives us a clue to different physical processes that are happening in the galaxy. So, this is our Milky Way, our own Milky Way, in different wavelengths. Let me just scan through this quickly. It's not a very good picture. Yeah, sorry about that. So, so this is optical. This is optical, and optical has a lot of problems because there's a lot of dust embedded in the gas, and the dust absorbs. So, optical doesn't always give you the right picture because a lot of radiation is being absorbed and attenuated. So, then you look at in infrared where the dust that was obstructing, the dust is also warm, that radiates. right? It's absorbing and it's getting hot and it's re-radiating in a different spectrum. So we look at infrared to get an idea of what was missing in the optical. Right? Then you look at, for example, this is radio and different wavelengths, which will tell you either molecules or the gas content. And this is, I think, this is the gamma ray, last gamma ray. Anyway, so I had more slides, but we'll stop here because now it is one thing to know that this is what the radiation that you expect. It's another thing to actually know how we detect this. That's also very important. Different wavelengths, you need to employ different technologies, different techniques. So that also is very interesting and is very important. And I'll just go through this because RRI has a tradition of building instruments, designing innovative instruments from radio to X-ray. I'm spanning the whole low energy to high energy, and I don't know whether they will go to some of the labs. Oh, okay. So you will see some of these, where they design and fabricate the radio receivers. So, for example, in radio, it's very easy. Radio signals are basically converted to electrical signals. And so, for example, one way to do is just a half-wave dipole. So I have a dipole, and the electrons, the wave will basically set the electrons in the antenna running around, and then basically you detect the signal. And we have in Gauri Bidnor, for example, these are dipole. These are basically dipole observatory, and this is 80 kilometers from. So this is run jointly by IIA and RRI. These are dipoles, and the dipole is now being also used in a very, very large array called low frequency array in Europe. So these are also dipoles. It's just simple dipoles. Okay, this is the Netherlands. It's a very large, and this is one of the largest low frequency radio telescopes now. You can also have dishes where you collect the electromagnetic spectrum, a wave in radio, and you have a receiver here. And I'm sure then in EEG you will get to hear more about it. This is a picture of the giant meter wave radio telescope near Pune. This is one of the largest radio telescopes in the world. And RRI has been involved very heavily in the designing of the receiver system for the 21 centimeter. Yeah, so this is another. Thanks for pointing this out. This is an interferometer, which means it combines the signal from several dishes in order to form an image, which is a very interesting thing with employing basically interferometry. And it acts like one single dish. You can actually make it do that using the rotation of the Earth. Okay. Then there are optical telescopes, and now, so basically this is a lens and mirror combination you use to get the electromagnetic wave to a focus where you put your detector. A detector can be a photographic film or a CCD now, right? And then you can also take some light out and put it into a spectrograph, get your spectrum, right? You need both. You need image and the spectrum. And these days, this is an example of the Keck telescope in Hawaii. It's a twin Keck telescope. You can see that this employs now adaptive optics, because if you want to get very high resolution, it's not very easy to get with ground-based telescopes because of the atmosphere, which blurs, right? So now they use segmented mirrors. The mirror is not one monolithic mirror. There are many segments. So they use a laser to find out the blurring that is caused by the atmospheric turbulence, and that on real time you basically change your the mirror is broken. It's made of different segments, and you can move up and down. So the electromagnetic wave that is coming, you think of the plane wave that is coming, is getting distorted by atmospheric turbulence, and then you use your deformable mirror to correct this and get it plane again. So this is what you would have seen in typical telescope without any adaptive optics. With adaptive optics, you can actually get a very high resolution, so which is now regularly used in very large telescopes. Okay. X-rays, we also have, we also produce, X-ray instruments in RRI. So in a nutshell, basically, this is a totally different technology. So you have a chamber where you have a gas here, and the X-ray comes and ionizes, and you have a wire here, so which then the ions basically come to the wire and then produces electric current. And the position of the electric current can, position where the photon has arrived or fallen, can also be found out through a voltage balance. Right? That's called the proportional counter. I'm not going to the details of this. You might, so my colleagues here have, you probably know that, in RRI we've fabricated a payload which is going to be launched very soon to detect the polarization of X-rays from astronomical objects. And this is the second of its kind, I mean, in the whole world. And the design is totally innovative here. It was indigenous. So I'll stop here with this picture that, when we use the multi-wavelength, it's like looking at, the story of blind men looking at elephant. So different wavelengths tell us different stories, and we piece together into a sort of total coherent story of an object or a phenomena. Thank you.
Thank you, Professor Biman Nath. I just have time for some quick questions. If there are any, the mic will go around. If there are any questions, we'll address them here. Please introduce yourself and then you can pose your question.
Sir, one thing I just wanted to know, this is the basic difference between that radio telescopes and this optical telescopes. Optical telescopes, what we teach the children.
Right.
Yes, sir.
No,
the radio telescopes and the X-ray.
Basic idea is the same. I need to get it to focus.
Yes.
Right. So I need to get the wave to a focus. But in radio, for example, the wavelength is much larger.
Okay.
So one difference is that I don't need to, the surface doesn't need to be so accurate.
Okay.
Okay, for example, just if you look at the difference between an UV telescope and optical telescope. The UV telescope, the wavelengths are very shorter than optical.
Sure.
So the surface accuracy has to be very, very high. In radio also, we are getting the waves into a focus. How we detect it, the detector that you put in the focus is different. There is just it just collects the voltage.
Okay.
And in optical, you would have put a film or CCD. CCD again, it's an electrical signal.
Okay.
So ultimately, it's an electrical signal.
Again, in detector, we use that tuned circuits again. We go for tuned circuits there.
Yes, yes. Oh,
yes,
so
sir.
in radio, of course, you have to tune it with
the
oscillator frequency and all that.
Yes, sir.
Right.
Thank you.
Thank you. Any more questions? There's a question here.
Very good morning, sir. Asal Manoj Paliwal. So one simple query. The time frame in which we are looking at an radiation, maybe from a supernovae or any other signals we are coming in, have a big time gap because of the distance to be traveled.
Yes, yes, sure.
So today we are seeking actually an image of what has happened in historical part.
Yes, yes.
How do we balance that thing? My
I
simple
just have
query.
to keep it in mind. That's all.
Okay.
The distance so what we're seeing now is what happened back then.
Earlier.
Yeah.
And by the frequency variations or Doppler shift, we can understand how back in the timeline would have happened.
Oh, if the object is moving, that will happen in the case of the expansion of the universe, for example, where the velocity is connected to the time.
But as we have seen that near field and far field, we are looking at multiple galaxies.
Right.
So that means we are looking at a different part of the universe at the same time frame.
Right.
So signal which we are
So if
focusing.
you're looking at a galaxy cluster, for example, you will see background galaxies. Yes, then you'll have to look at its redshift, and that will tell you the time when the radiation that you're getting now was emitted.
So actually my question is ki how, when we have a mapping of all those things in the astronomical space, ki bhaiya this galaxy is somewhere here, this cluster is somewhere here, that is what we are expecting as of now based on the signal we have received now.
Yeah, that is the position that was there when the light was emitted, not now.
Agreed.
We
That's the
can
point.
never figure that out.
But we can predict it to the back by going
If you
back
have-
in a computational
If
methodology?
you know the model of the universe, if you claim to know the model of the universe, which who knows?
Who knows? Thank you, sir.
You know.
Thanks a lot. But a lot of like we are not very sure what we are looking at,
Yes.
but we are analyzing the data in present scenario. We are knowing it is in the historical part.
right.
How much?
We know what we're looking at such certain epoch in the past.
Agreed.
That's it.
Okay.
As long as we're clear about that, that's fine.
Okay.
And yeah.
Second query regarding the same thing. For lower wavelengths, we go in space. For higher wavelength, we have telescopes and other analytical devices, like you said in Cuba, we have in Hawaii. That are for longer wavelengths, we have like GMRT. It's a longer wavelength instruments.
Yes.
And shorter wavelength, we need to slightly go above the space and Chandra X-ray and all those things.
If you go to very, very longer wavelengths also, you need to go to space also because of the
Okay.
ionosphere. The ionosphere is going to block.
Okay.
Which is how the radio signals are, radio broadcasting happens, because they get reflected. But if you look at it from a point of view of an astronomical object, it's like a metal sphere, right? The ionosphere. So the radio waves transmitted from the ground gets reflected and comes back.
Okay.
But a radio wave coming from astronomical will also get reflected and go back. So we will not be able to see that.
So shielding of both sides.
Yes. So, for example, in RRI, we are thinking of going to the moon. So there are ideas of putting things on the lunar orbiter so that we can go even longer wavelengths.
Thank you. Thanks a lot, sir.
Okay, I have time for one last question, and thereafter maybe we can take the discussions during the tea time. I love to allow the person. Maybe you can ask during tea time, Professor Nath will be
Sir,
available.
good morning, sir.
Morning.
Sir, can you say something about James Webb telescope, sir?
Ah,
Which is at
that
L2
requires
point,
the whole.
point L2.
Yeah.
We would like to know point L1, L2, and why it is positioned in L2, sir. Can you say something about, because just now you told that mirrors are used.
Yeah, that's a very stable as far as I know. Correct me if I'm wrong. This is supposed to be a stable configuration, right? Which is where it was sent. And also so that it's far from Earth's glow, or I don't know. I mean, what was the exact consideration for L1? But the fact that, you know, it's the largest space telescope that we have now, and it's looking at infrared, is opening up a totally different window. And every week there are papers after papers of, you know, totally new discoveries, and it's going to happen for next 2 decades. So astronomy is going to explode. It's already exploding. I think this is the most exciting part of physics, field of physics.
All right. So I hope the teachers take away astronomy as a tool when you all go back and teach lessons in your schools. So once again, let's thank Professor Biman Nath for this time. Thank you.